Who has the fastest reaction time?
Me.
Girls or boys? Are girls better than boys, or are boys better than girls?
I'm always ants on caffeine, so. Yeah.
And we're going to use statistics to analyze our answers. Okay?
It's not that bad. Let's go with like ice salt. Meet in the middle.
So, here's what you do first thing. You go to Google. Y'all ever heard of this?
Maybe.
I've never heard of it.
It's like the most powerful company in the world. Alright, you go to Google and you type in reaction time test. Reaction time test. We're going to do a little experiment. Reaction time test human benchmark is the one you need. When the red box turns green, click as quickly as you can. Click anywhere to start. So watch me do it before you do it. Okay, so I'm going to click to start, wait for green.
Ooh.
Click to keep going, wait for green.
Ooh.
Click to keep going, wait for green.
Ooh.
Click to keep going, wait for green.
What if you click before it's
Click to keep going, wait for green.
What if you try to like jump the gun and click early?
Okay, so save your score to see how you compare. So I'm going to put save score. So this is my average. This is my average. Look, I'm 25th percentile. I have slow reaction time. You know why I have a slow reaction time? Because I'm old. You probably do better than this. So, play that game. Keep your score. And then we're going to make a little graph of the results. So go ahead and do that. Everybody's got to play the same game, or it won't be good. We've got to do the same reaction time test.
Look at the bell curve. My reaction time would be impressive.
Oh, mine's really slow. Stop.
Wow.
So stressful.
Just calm D.
So bad.
How many do we do?
Mine's slower.
You just keep doing it until you get your final answer.
Mr. Willis, I'm like way
Oh,
slower
no.
than you.
Yeah, me too.
Yeah.
Maybe I'm wrong. Maybe I am.
Oh, wow.
Or something better. Are you filming this, Lottie?
Yes, sir.
10th percentile. What's up?
I'm in the 6.5.
Guys, you're doing this on a laptop.
Yeah.
Make it a lot harder.
So do you want us to like write that?
Write the number down.
No, I think you can get like 90%.
304.
Just or remember it. So I'm going to make a table. Boys.
I had to catch it.
What are you?
This is reaction time test.
I'm 16.8.
Let's
What
see.
are you
doing?
16.8.
Wow.
Percentile.
Do what?
I'm in that 60.
Okay, so I'm going to put down mine. Mine was 280. This is
Can we not count yours, Mr. Willis?
Why?
Yeah, yours is
If I was
fast.
competing with snails, my reaction time would be impressive.
okay. Let's not count mine. All right. So all the boys, tell me what you got.
Andrew's over there.
I don't think I would.
Alright,
What's up, Andrew?
293.
293.
Done.
It's all like 304.
304.
303.
303.
You guys are slow.
Any more boys?
No, we never
302.
fine.
302. Anyone else?
339.
That's like literally like my hammer shake.
Is that all the boys? Okay, girls. Tell me what you got.
339.
339.
Seriously, has to do it now. 247.
247.
No, I call bull. I call bull.
That's cap.
She's on the map book.
Yeah, I feel like the map book's kind of an advantage.
Alright, I need other scores for girls.
Shoot.
285.
We should
Give me that.
Actually,
I mean,
if you think about it, we have to go farther down.
Can y'all stop telling me we gotta do this? Somebody tell me, girls, tell me your numbers.
315.
Okay?
362.
316?
62.
362? Check.
Yeah. I'm craving corn credit roll on that one.
352.
352?
Oh, really?
329.
329?
I got the high score.
Anyone else?
Alright, never mind.
Is that all the girls?
Yeah.
Is every girl's up here?
Okay.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's only 11 numbers. Somebody didn't tell me their number.
Julie?
Oh, because you don't have a computer?
Yeah.
Julie.
Silly goose.
Do you have a computer anywhere that you can go get?
You did not just do the exact same number as me.
Just do it real quick.
You don't have to do the test. No. You need your own computer to do the graphics. All right. We'll just use these numbers. This is good enough. So, what you have to figure out is something called the standard deviation and standard error. You have to understand what that is. So, there's a formula. Let me show you the AP Biology formula sheet. Have y'all seen this before?
Yes.
So look at the standard deviation formula. Isn't that formula intimidating?
Nah.
You're probably going, there's no way I can understand that.
That's exactly how I'm going.
And you remember?
So let me explain to you how this works. So, how do we figure out the standard deviation? Although the formula looks intimidating, it's really not. You need to understand these symbols. S is the standard deviation. Y'all know this symbol, right?
Square root.
Square root. Okay, that's fine. What does this symbol mean?
Summation.
The sum of. That means we're going to add things, sum things together, add things together. So, xi and x bar, what do those mean? Xi stands for sum, for your measurement, your number. Okay? Can you? We're gonna figure this up for the guys first. Can y'all? Let me go back. Let me write the guys' numbers down on the board so I can show you how to work on this. Okay. So the guys' numbers are 293, 304, 303, 302. All right? So we have four numbers here. So when we say xi, we're talking about one of the numbers. And when we say x bar, we're talking about the mean. X bar means the average. So you take your number and you subtract the average. So we got to average all these together. Do y'all know how to do an average on a spreadsheet? Let me show you how. Here's all the things. If I want to get the average, I'm just going to put a little box here that says average. All you got to do is put equals. Oh, and it just gives you that choice. Equals average, open parentheses, whichever numbers you want, close parentheses.
That's the average.
That'll give you the average. That's an equation you can type in on a spreadsheet for the average. Let me break it down for you. Equals average, you type in average, then you put open parentheses, and then you just highlight the numbers you want. Now I'm going to go all the way down to the bottom here because I want to get this average too. So I highlight all these squares. It's not gonna do any math for the empty squares. And then I put close parentheses. And then I hit return and it'll give me the average. That's the average for the guys. Now if I want to do the same thing for the girls, there's an easy shortcut. I put my arrow over this square, and then I left click, and I can just pull that over. And it'll get the average for the girls. Now look at all these decimal points. You shouldn't have that many decimal points there. You don't know it to that precision. Look at all our measurements. These measurements were all rounded off to the nearest unit. So I got to do the same thing with my answer here. So I'm going to lower the number of decimal points. Do you know how to do that?
Press that button.
You press the decrease.
You go up here, decrease decimal places, and I just click on that, and it makes it go down. Do you see what I'm saying?
Yes.
You could also increase the decimal places. Every time you push it, you go up decimal places.
Keep going.
But we don't want to do that. Okay. So here's the boys' average, here's the girls' average. So does that mean girls are slower than guys?
Well, they
Not
have less
necessarily.
people.
Could be standard.
Ooh, Joseph brings up
Small
a good
sample
point.
group.
Yeah.
Is that the word?
Notice the boys have less. I mean, that gave us an average of 301, but what if we just happen to have 4 fast reaction time guys? Maybe that, or maybe we had a couple slow reaction time girls that skewed the average. How can we statistically analyze this evidence? What we have to do is get a measurement called the standard deviation. So, back to the formula. Back to the equation sheet. The standard deviation is the sum of xi minus x with a bar over n minus 1. So what is n? N is the number of measurements taken in the group. So n would be 4 for the guys, because we did 4 measurements. So 4 minus 1. So let's plug this in and figure it out. So let me show you how to do this first part. Xi minus x. So Xi is our first measurement, 293. X bar was what? What was the average?
301.
301 was the average. So 293 minus 301. What's 293 minus 301? Any state championship math teamers in here?
-8.
It's -8. So -8 is xi minus x bar. It's -8 for our first measurement. But do you see how it has the sum of? You got to go through and do it for each measurement.
You have to square the difference.
So, I left out the square. Whoops. I left out the square. Thank you. That's important. So, what's -8 squared?
64.
Or not 64. 64.
64.
So confidently.
Andrew.
Yes.
Good job. Sticker for you. Star for you.
Yeah.
All right. Let's do the second one. 304. Let's get rid of the 293 and do 304. What's 304 minus 301 squared?
3.
304 minus
9.
301 is 3. What's 3 squared?
9.
9. So 9 is our second number. And then let's put 303 in here. What's 303 minus 301 squared?
4.
4. Are y'all with me?
Yes.
And then the next one, 302.
1.
302 minus 301 is 1. 1 squared is 1. 1. And we're going to sum all that up. 64 plus 9 plus 4 plus 1. 73, 74, 75, 76, 77, 78. Are y'all with me? That's great, isn't it? This is math. So we get 78 at the top of our fraction after we do all this math. What's at the bottom of our fraction? N minus 1. N is the number of measurements. 4. 4 minus 1 is 3. What's 78? What's the square root of 78 over 3? That's what we want to figure. Can anyone do that for me? Ask Siri or something. Take your phones.
You want decimal?
We'll go to one decimal place today.
5.1.
5.1?
Yeah.
Okay, Mr. Calculator.
Thank you, Mr. Calculator. Okay, so 5.1 is our standard deviation here. That's the standard deviation for the guy. Now, what does the standard deviation mean? The standard deviation is a number that tells you how far away your measurements are from the mean, on average. Yes?
If we had more people, would the standard deviation go up or down?
It depends what the other measurements were. If the other measurements were close to the mean, your standard deviation would go down. If the new measurements were far from the mean, the standard deviation could go up. But generally, the more measurements you have, the lower well, it wouldn't necessarily go up or down. It depends on what the measurements are.
Greater variance causes more measurements.
Greater variance causes a higher standard deviation. So this is a number that represents how far the measurements are from the mean. So for instance, do y'all remember the bell curve that I talked about yesterday?
Yep.
Here's the mean is in the middle, and most of the measurements are around the bell curve. If your standard deviation is low, let's say the standard deviation is only 1, that means almost all the measurements are right near the mean. A low standard deviation would produce a bell curve that looks like this. Almost all the measurements right near the mean. That's a low standard deviation. A high standard deviation, let's say it's 50, I don't know, would produce a bell curve that looks more like this. You see what I'm saying? That means the numbers are real spread out. They're not near the middle. That's what standard deviation tells you. How bunched up your numbers are or how spread out your numbers are. The lower the standard deviation, the more bunched up the numbers are. The higher the standard deviation, the more spread out the numbers are. Okay? And so, whenever you report a mean in an experiment, you also need to report the standard deviation. Okay? So, that tells the person that looks at your experiment, oh, their numbers are really bunched up together, or oh, their numbers are really spread out. So the guy's standard deviation was 5.1. Now let me show you how to do this quickly using a computer. Computers can do the standard deviation real quickly for you. You don't have to do this hand math each time. Whoops. Go back to this. How do we find standard deviation? You just put equals STDEV. Oh wait, I don't want to do it there. Equals STDEV, open parentheses. I'm going to highlight the boxes I want, close parentheses. Bam. We got 5.1, didn't we?
Mm-hmm.
Well, it didn't quite round to 5.1, so I'm going to do less decimal places. Less decimal places. There we go. You like it? Now, do you remember I could just drag this over one and get the girl's standard deviation?
Nice. My calculator did it.
Now, the girl's standard deviation is a lot higher. What does that tell you?
How wide is that close?
That the girl's measurements were not real close together. So somebody can look at your average and your standard deviation and know more about your numbers.
You guys went right on that one. Too fast.
Do it, Greta.
Real new curve.
What is it?
Now,
It's not my curves that we're getting.
so this is the standard deviation. Now we need to, you need to know about something called standard error. Whenever you do a graph of your results, you have to include what's called a standard error. Now this would be a good bar graph. Let's do a bar graph of the results. So let me do the graph first. I'll simply go here. I'm going to make a new column here. Boys reaction time in milliseconds. Girls reaction time in milliseconds. There we go. And then, so the boys was 301, and the girls was 318. And now I'm going to highlight these so I can make a graph. I'm going to do insert chart. Sometimes you have to uncheck these boxes to make it work. So, here is my chart. That's what my graph would look like. Okay?
It's on the x-axis.
That's not right. I can change that.
Why not?
See, I can go to
Horizontal axis.
I can go to chart and axis titles, horizontal axis title, and I can put boys and girls.
Ooh. And snazzy.
You like that?
I like
the average and standard deviation.
What?
There we go.
Average.
Okay, so check this out.
Now you gotta change your y-axis.
Most anyone would look at this graph who doesn't know anything about statistics, and they could say the boys have a faster reaction time than the girls.
Your y-axis is still funny.
Oh, you mean the title?
Steal my fame. Steal my fame.
Should just be milliseconds.
You know, I actually noticed it too.
Oh, I said
Did you
something.
say it?
I said something first and Tiff just stole it.
Thank you, Chad.
You're welcome anytime.
All right, so now we got it. So if you didn't know anything about statistics, you would say that the boys are faster than the girls because their column is shorter. But we have to do a statistical analysis, which I think is going to prove that incorrect. How do we do that? We have to find what's called the standard error. Let me make this smaller. Move it over here. How do we find the standard error? Well, the standard error, if you look at the formula sheet, it's an easy formula. Standard error of the mean. The standard error, it looks like sex, y'all. It's funny. See how it says S-E-X? That's actually standard error of the mean, because actually the bar over it is the mean. But most people look at it and they go, oh, it's sex. That's hilarious.
It is kind of funny.
Well, you need to just calm down. What it is, the formula is the standard deviation, S, the standard deviation divided by the square root of n. So how can we get that for our guys' numbers? It's the standard deviation, which is 5.1. And I'm going to just do my math in the block here. 5.1 divided by the square root of, how many measurements did the guys have? 4. Divided by the square root of 4. Do y'all know what the square root of 4 is?
2.
God, y'all are good.
About 12.
So it's 5.1 divided by 2. That's the standard error for the guys. So it's 2.55 is the standard error for the guys. Now what's the girls' standard error? It's the standard deviation 40.4 divided by the square root of how many? 7. 7 measurements for the girls. That's 318 is the mean. So they have 1, 2, 3, 4, 5, 6, 7. So it's 40.4 equals 40.4 divided by the square root of 7. I'm just going to do the square root of 7 on my calculator. It's 2.65. And here's the standard error for the girls. 15.2. So the girls have a much higher standard error. Why? Because they had a higher standard deviation. If your standard deviation is high, you're going to have a high standard error. What the standard error is the confidence in your mean. How confident are you that the girl's mean is what it is, or the guy's mean is what it is? That's what the standard error tells you. You have to calculate the standard error. It's a statistical measurement, and what it'll do is it'll give you what's called error bars. Have you ever seen error bars on a graph?
Yippers.
If you ever see a bar graph, if there's been a statistical analysis of it, you'll see an error bar on it. That means there's been a statistical analysis of the data. And it looks like a capital letter I. And what it means is that we're not really confident that the mean is actually right there. The mean could be way up here. The mean could be way down here. Now, you don't actually take the standard error and put it on your bar graph. You take twice the standard error. Twice the standard error gives you a lot of confidence. And it's a statistical thing. If you take statistics, you'll study it in more detail. But if you put your error bar at 1 times the standard error, that's a 66% confidence level. If you put your error bar at 2 times the standard error, if you make it go twice as big, that gives you what's called a 95% confidence level. In other words, you're 95% confident that the actual mean falls within this range. You're only 66% confident that the mean falls within 1 standard error range. And again, you have to take a statistics course to really understand the mathematics of it, and that's beyond this course. All you got to do is be able to figure it. And so we got to take twice the standard error. So the standard error equals this. Let's make it 2 times the standard error. Or 2 times SEX. 2 times sex, y'all. So what's 2 times 2.55? Any state championship math teamers out there?
5.1.
2 times 5.1, which is actually equal to our standard deviation, which makes sense because we have 4 measurements. What's 2 times 15.24? 30.4? 30.5? Okay. So, now we have our standard, our boys' standard error and our girls' standard error. Now we're going to put that on the graph. Let me show you how to do error bars on a graph. How do we do it? We click on this bar. There we go. Click on this bar. Here we go. And you go to error bars. It gives you a menu, and you can put error bars in it. We don't want to put a percent. We want to put a constant value. And that constant value is, what was it for the guys?
5.1, I think.
5.1, that's right, 5.1. So it's got a little error bar there. Can you see it? It's little. You can barely see it. I'll make it bigger so we can see it better. Let's do it for the girls. Okay, error bars for the girls. We don't want a percent, we want a constant value. What was that value, do you remember?
30.4.
30.5? There's the error bar for the girls. Now, let's make this graph a little bigger. Graph a little bigger. There we go. Can you see the little error bar for the guys and the big error bar for the girls? Now here's the takeaway from this. Do you notice how these error bars overlap one another?
Mm-hmm.
The bottom of the girl's error bar is below the bottom of the guy's error bar. And the top of the girl's error bar is way above the top of the guy's. And the most important thing is, the bottom of the girl's error bar being below this means the girls could be below the guys. The girls could be faster than the guys. There's no way for us to conclude from our experiment that boys have a faster reaction time than girls.
You'd have to do a lot.
And what you would say, and they're going to ask you this on the AP exam, what you would say is, there's no difference between the two groups.
What if they
Statistically, there's no difference between the two groups. That's what you have to say. You can't say the girls might be slower. You can't say anything like that. You say, according to our data, there's no difference between the two groups if the error bars overlap. Yeah.
That's what I was about to say.
If the error bars overlap at all, if here's one error bar and here's the other, and there's even barely a little bit of overlap, then there's no statistical difference between the groups. That's how you say it. There's no statistical difference between these two groups. And what you would have to do is maybe redo your experiment and get more measurements. The more measurements you get, since you're always dividing by the square root of n, the more measurements you get, let's say we did 100 measurements. Then what are we dividing by? What's the square root of 100? You're going to be dividing by 10 instead of dividing by 2 for the guys. And dividing by 10 for the girls if you had 100 measurements. Instead of dividing by whatever it was, 1 point something. Or 2 point something. If you can get more measurements, you can make your error bars go down in size.
Then why were the girls' error bars, or why was ours so bigger?
Because y'all had such a high standard deviation. You had some big measurements, some small measurements.
But wouldn't that still happen if you did a large group?
It could. You could have that, but if you got a lot more people, you make that standard error go way down by having more people. That often happens in experiments. This is why it's not good to do an experiment with just a few trials. You can never come up with real good conclusions to show that there's differences. If you got 100 guys and 100 girls in your experiment, you may be able to show those error bars don't overlap, and you may be able to show that guys are faster than girls. I don't know. But they're going to throw this at you all the time in AP Biology. They'll show you an experiment, and they'll have error bars that overlap, and they'll ask you to draw a conclusion, and you have to be able to do that. Okay, stand up for a minute and come into this next, come into the lab, and let me just show you.
Hello.
Come on in here. We have 3 sets of measurements here: light, room, and and dark. Okay? What we concluded, do you remember making a conclusion on this?
Yes.
The light had more transpiration than the room, and the room had more transpiration than the dark. Do you remember that? You didn't statistically analyze that data. Okay? I want you to do that. So what you do is you take these numbers, you'll have them written down in your logbook.
Yes.
Take those numbers, you plug them into a spreadsheet, you find the standard deviation, standard error, and draw error bars on your graphs. Yes.
To do the math, or can you plug it in there?
You can use a computer to do the math. Do y'all see? And then you'll have a graph with 3 error bars, and this will be light, room, and dark. Did you already make this graph? Do you remember making this graph
We
already?
made it without the error bar.
We made it without the error bars. So all you're going to have to do is add error bars.
That's fine.
And you can hand draw them in there if you did your axis correctly, or you can print it out on a graph. You can do a graph on the computer and put your error bars in on the graph and then print the graph out if you want to. But you can always just hand draw the error bars in. If you have your units on this axis correctly, you can figure out 2 times the standard error and hand draw them in. Do you see what I'm saying?
Mm-hmm.
Ja feel?
Feel job.
Okay, so go right now. Do you have your logbooks?
Yeah.
Go get your logbook and try this. Try it right now. Got about 10 minutes left. And Willis is out.